So this week, we're going to be finishing up last week and talking about like these trig identities. So we're going to finish up sines and cosines, talk about trig identities, which you see on that sheet that's posted on Blackboard. It's the main focus, and inverse trig functions. Now, suppose we have theta is between pi and 3 pi over 2. And we have tan is equal to 4. Evaluate the cosine of theta and the sine of theta. Okay. So we could kind of draw this out on the unit circle. This is our unit circle. 1, 1, negative 1, negative 1. So theta is going to be between pi. So here's pi, because the whole unit circle is 2 pi, and 3 pi over 2. So it's going to be somewhere over here. We're not sure where our theta is. That's our angle. Now the tan of theta is equal to 4. So by definition, we know tan is sine over cosine. So this is equal to 4. Now, when you draw it on the unit circle, what do you notice? You observe something. So we can see that both, if you first just observe where it's theta is defined, we see that both cos of theta and sine of theta are negative. Because remember, like this point here just means cos of theta and sine of theta. This is our x and our y pair in a sense. X is cos theta and y is sine theta. Okay, so we know the identity, the main identity we learned was cos of theta squared plus sine of theta squared equals 1. And we want to evaluate cos of theta and sine of theta. So I'll just rewrite it. So cos of this theta squared plus sine of theta squared is equal to 1. Now we can just substitute and rearrange for this. So we could say sine of theta is therefore, if we cross multiply, is equal to 4 times cos theta. So let's just substitute that in to the identity. So this would be 4 times cos of this theta squared equals 1. Now 4 squared, we're distributing this out. So cos theta squared plus 16, because it's 4 squared, 16 times cos theta squared equals 1. So this implies, now we group like terms together. So we have like, let's say cos theta squared, that's kind of like our x, and we have another x. So we have 1x plus 17 or 16x equals 17x. So this is 17 times cos of this angle squared equals 1. Then what do we do? Because it's a squared. And I'm just going to write some notation over here. So special note, before I get any further, cos of theta squared is equal to, we can rewrite it this way, the cos 2 between the cosine and theta. It means the same thing. And the same with sine and tan and whatever. So sine of theta squared is equal to sine squared theta. Like you can bring it inside. You don't have to write the brackets each time. So it's just a simpler, easier way to write it more smooth. So this just means like we have two cos times cos is cosine or cos theta squared. So we can divide by 17 on both sides, the left and the right side. I'll continue with this notation and then take that square root. So it'll be plus or minus square root of 1 divided by 17. Okay, so is it plus or minus? Well, back to the picture of the unit circle, you see that it goes from 180 degrees to 270 degrees. This is like our 180. This is our 270. And the cos is negative, right? Because it's going down the y-axis. So therefore, this one's just going to be negative. Now, it says also evaluate for sine. Once you're like done a question, so always go back and read the original question. Make sure you actually answered it. We have to evaluate the sine of theta. What is the sine of theta? Well, it's 4 times the cos. So we know the cos, so we have the cos. It's negative square root of 1 over 17. So it's going to be, sine is 4 times cos. So this is going to be negative 4 times square root of 1 divided by 17. Now, the domain and range of tan. So tan by definition is sine divided by cosine, whenever cos does not equal to 0. So cos equals to 0 as specifically when theta is equal to pi divided by 2. So at 90, and we could go back and like look at the cosine graph, the sine graph, and see when the cos is actually equal to 0. So like, this is why it's good to draw that graph. 3 pi divided by 2, 5 pi divided by 2, and so on. There's more. We could write more. Negative pi divided by 2, negative 3 pi divided by 2, negative 5 pi divided by 2. So when basically the cosine of theta is close to 0, so when this cosine is closer and closer to 0, so the denominator gets smaller, tan can get large. So when the bottom gets smaller, the tan gets a much larger number. And so, and it can't equal like these specific values, theta. So the range of tan can go from negative infinity to infinity, because it could go from very small numbers to very large numbers, but it can't actually equal like these specific values. Okay, so let's try to draw tan. Of course, you could check Google or something like this, or Desmos. So this is on the x-axis here is theta, which is in radians. And this is going to be our tan theta. Now it can't equal like those specific values. Can't equal pi divided by 2, so on. So we can label them on our graph. Not equal. Let me move over. So it won't be this value. Won't be 3 pi divided by 2. It won't be 5 pi divided by 2. Also said it wouldn't be negative. And you can, of course, compare it again. I'm just repeating myself to that cosine graph. Now I'm just labeling some other points like pi, 2 pi, negative pi, negative 2 pi. It's not drawn to scale, sorry. The first part is, I made it a little bit too wide. Anyways, it goes up like this. Oops. And at pi, it starts at 0, and then it goes up, and then down, up, and then down. Sorry, I squished it. I made it too large, the scaling in the center, and I squished it at the ends. So, but this is the idea, and I really apologize. It's not drawn. This part, the scale, this is squished. This is too wide. Sorry. I'll try to redo it another time. But you can plot this, and you can see like kind of the pattern is the point. You can see that we have these asymptotes, these vertical asymptotes. Before we were talking about horizontal asymptotes. So the point is, and I'll try it in another color here. We have vertical asymptotes. At like these specific values. So when theta is equal to these specific values, tan does not exist. It is undefined at those specific values. And what other observations can we see? Another observation is that we see that tan has a period. So it's periodic with, well, it repeats every pi. Like before sine and cosine repeat every 2 pi. Tan repeats every pi. So it repeats with this period of pi. because you see, you start from negative pi divided by 2 all the way to pi divided by 2. Or from like 0, you could pick any points from that, like let's say have this symmetry. So from 0 to pi, it repeats. From pi to 2 pi, it repeats. There's this repetition. Sine and cosine, remember, it repeated every 2 pi. So that's just the graph. There are 3 more frequently used trig functions that can be derived from cosine, sine, and tangent functions. This is secant. Secant, by definition, is 1 divided by cosine. So this is secant. Cosecant is 1 divided by sine. And cotangent is 1 divided by tan. We know tan is sine divided by cosine, so we just flip this. So that's going to be cosine divided by sine is cotangent. So we can evaluate these. So let's evaluate them together. So the secant of 60 degrees is going to be 1. Let's go back to our definition. 1 divided by cos. So 1 divided by cos of 60. Now, so 1 divided by, remember I gave you, it's online, but I said like that you're going to have this sheet for your final exam. So you could look this up on your table if you wished. So the cos of 60 degrees is going to be 1 divided by 2, which is 2. Now the cosecant of pi divided by 4. By definition, it's 1 divided by sine of pi divided by 4. So it's 1 divided by, we can look up pi divided by 4 on the sheet if we wish. It's a square root of 2 divided by 2, which is the same as 1 times 2 divided by square root of 2. We did this before, which is just 2 divided by square root 2. And we could simplify this if we wish. If we didn't want the square root of 2 on the denominator, this is the same thing as square root of 2. And you could do some math to figure this out or try on the side. And cotangent of pi divided by 3 is just 1 divided by tan of pi divided by 3. By definition, it's cos of pi divided by 3 divided by sine pi divided by 3. We can look these up again on that sheet. If so, this is 1 divided by 2, and this is the square root of 3 divided by 2. And then we simplify. The 2's cancel. I get 1 divided by square root of 3. Remember, there is that sheet, do print it out so you can start practicing your assignment 3, etc. Help you for your final. Now, so trig and right angles. So consider this unit circle, and the radius that, like, let's say there's an angle. Let me draw this. I've drawn it several times. Sorry, I'm just putting axis through our unit circle. So this is 1, 1, negative 1, negative 1. So suppose we have a point on the unit circle, let's say here, and it has like specific coordinates. We know it's going to be cos of this angle, sine of this angle, theta. And our radius is 1. So we can draw a right angle triangle with a circle. And this is our angle theta, taken near the origin there in this specific example. This is our cos, and this is our sine. So nothing new, we've done this before. But I'll draw a larger picture here. So we have a 90 degrees here. We have theta here. So across from theta is our sine of our angle. This is 1. Across from this angle over here, well, this angle is going to be 90, subtract theta. And across from it, it's going to be cos of theta. So notice like it's across from each other. I'm just rewriting it one last time. Actually, one more time. So we're going to do similar triangles. Let's write a really large triangle. So this theta, let's say across from it is B. Across from 90 degrees is C, and across from this angle over here of 90 degrees minus theta is A. So notice the pattern. So the cosine, if we go back to our similar triangle, this cos at the bottom here is equal to A, and C is equal to 1. We can do like ratios in similar triangles essentially. And this is how we're going to like analyze it. So we're considering like basically similar triangles. They're both similar. They're both 90 degrees. They both have the same angles, but they have perhaps different lengths of sides. But as long as they're similar triangles means the angles are all the same. So it means corresponding angles of two triangles are equal. So because they're similar triangles, we can invoke this power of ratios to analyze the similar triangles better. So this is, sorry, I'm going back and forth. So we have the cos on this side is equal to A, and 1 is equal to C. And because the angles are the same, we can play with these ratios. Here we have sine is equal to B, and 1 is equal to C. And then, so we have like these. Then we can have tan is obviously going to be sine divided by cosine. So it's A over C divided by B over A over C. No, sine is going to be B over C divided by cosine. Cosine is A over C. So the C's will cancel and you get B over C. You should kind of be able to see that like looking at it. Let me make a little note about similar triangles. So similar triangles just have this property that the ratios are basically similar of the corresponding side lengths are the same. It doesn't mean the side lengths, it means the ratios of the corresponding side lengths are the same. Doesn't mean the side lengths are the same. And this allows us to do like mathematical modeling. As long as you get the ratios in proportion to things, you can relate it to something much larger like the Earth or whatever. You can do a model of it much smaller. Okay. So then we would have like these characteristics, but let me first write this all down and kind of repeat it. So the cos of theta is equal to A over C. Sine of theta equals B over C. And tan of theta equals B over A. So I'm just rewriting it. So C here is our hypotenuse. This is B, this is A, this is our theta. B is opposite to our angle, which is important. A is adjacent to our angle, like right beside our angle. This is our adjacent side. This is a right angle triangle. So as you can see, right triangle. So why do we get this? Yeah, so you see if you simplify, you get a cos of A over C. A is this adjacent side divided by C. Sine is the opposite divided by the hypotenuse. And tan is opposite divided by adjacent. So this works only in the case of, well, for any real right triangle. Is there an easier way to remember this? Anyone? Yes? Right, SOHCAHTOA. So let's just write that down. So SOHCAHTOA. So it's always easy. So how do you remember? Sine is equal to opposite over the hypotenuse. Cosine is equal to the A is adjacent over divided by hypotenuse. And the tan is equal to opposite divided by adjacent. Right? You should know SOHCAHTOA. Has everyone seen SOHCAHTOA in high school? Good. Okay. So let's do some questions, right? So the side of a right angle triangle, so let's draw a triangle. And it's right angle, so we know it's 90 degrees. And we have the lengths are 3 and 6 units long are the sides. So this is 3 and 6 because they're the sides. And the angle opposite to the side of length 6, so the opposite one is theta. Okay. So first, just like label our triangle. First, find the lengths of the hypotenuse. So this is our side C. Just going to label it. and use that to evaluate cos, sine, and tan. Okay, so we could find this. How would we find it? See? Yes? Pardon?
Our first step would be a squared plus b squared plus c squared.
Right. Right, perfect. So our Pythagorean theorem. So c squared equals a squared plus b squared. And then we just calculate. So 6 squared, 36 plus 9 is 45. So C is going to be plus or minus square root of 45, but it's a triangle. It can't be negative. So let's remove that negative sign. So this is going to be square root of 45. Now we do the cos, sine, and tan. So cos of theta is just adjacent. I always like to write SOHCAHTOA in the corner. It helps me remember. So the adjacent side is the side closest to the angle. So that will be 3 divided by square root of 45. Then we do the next one. Opposite. I'll just write SOHCAHTOA over here. So this opposite is 6 divided by square root of 45. And tan is opposite divided by adjacent. So 6 divided by 3, which is 2. So we know the slope of this, because what is tan, by the way? Do you remember? Tan is the slope. So we found tan equals 2. So therefore, the slope of this line is actually 2. More questions. So the side of a right angle triangle. So let's draw a triangle first. And it's right angle, so I just like to label it 90 degrees. So the side of a right angle triangle opposite to 28-degree angle is 4 units long. So this is 4 units long. Opposite would be 28 over here. Find the lengths of the other side of the triangle and the hypotenuse of it. So find this. Let's label it C. We could label this A. Okay, so I like to write SOHCAHTOA. And think about, what do I have? What could I use? So I have the angle. I have a side over here. I want to find maybe another side to start off. You could probably use anything. You could do this question probably other ways. So the tan of 28 degrees is equal to opposite over adjacent. But here, our angle is up here, it's 28. So this is going to be our adjacent because it's the closest one beside our angle. So opposite is 4, adjacent is our A here. We could use a calculator. So what is the tan of 28 degrees? Using a calculator. Anyone? If you just punch it into your calculator, 28 degrees. Pardon? Tan of 28. Is it in degrees? Got like a 0.53. I just ask you because it's good that you're calculating along with me, like you're not passive, that you're, because on the test or the quiz, you're going to have to calculate something. So suppose we get 0.53. So this implies 0.53 is equal to 4 divided by 8, which implies 8, if we cross multiply, A times 0.53 is equal to 4. So our A is therefore, divide the left and right side by 0.53. We get 4 divided by 0.53, which is approximately equal to 7.5. So this side is therefore equal to almost 7.5. So I like to label it. Then we can, of course, find our C. I'll just leave that for you. I'll just make a little note here. And I'll leave that as an exercise. Just do, A squared plus B squared equals C squared. Okay, another question. So I'll give you a second to read it and work it out with me. I'll just draw the triangle. So you have a surveyor at point B here, wishes to measure the distance between points A and B. But there's a canyon between A and B, and it prevents this direct measurement. Thus, the surveyor moves 500 meters perpendicular to line AB. So we know if it's, this is our line AB, they're moving perpendicular. So they're moving either up or down, but they're moving perpendicular. So let's go up to this point C, 500 meters. And then they measure this angle BCA as 78. So this angle here is 78 degrees. So what is the distance between A and B? So what is this angle? So we know this is going to be 90 degrees because they move perpendicular. This is 78. We know this angle here is 12. Okay. So we want to find X essentially. And we could just, there's this canyon here. So find x. Huh. So do we want to use sine, cosine, or tan to solve this problem? If we have this angle 78 and we want to use that. Tan, right? Because we don't really have this side from C to A. We don't have that length. So this is why you would probably go for tan. So I would write it out like I would write SOHCAHTOA, and then I would think, do I want to use sine? No. Do I want to use cosine? No. Tan fits our question here because we don't have this particular side. We have 500 meters, we have x, so this lends itself to our tan of this angle is opposite over adjacent, or O over A, if you like to write it. This is our opposite. This is our adjacent. Okay, so now we can write this. 78, tan of 78 is equal to opposite, our x that we want to find, divided by 500. We can use the calculator and solve. So we find that basically tan 78 degrees is approximately equal to 4.7. So this implies 4.7 is approximately equal to x divided by 500. You could even rearrange this first. So this is 500 times tan of 78 degrees. That's an easier way too of doing this. Cross multiply, get 500, 4.7 times 500. It's approximately equal to x. So this implies x is equal to, anyone? Punched it into your calculator. What did you get? Right, 2,350. I'll just put that because I know physics, you round to 3 places. Like here you have 500, 1, 2, 3. So your answer should be 1, 2, 3 digits. So this is why it doesn't matter. So we could just, so we found x. So our x was approximately 2,350 meters. Okay. So identities. So we've just seen like this very important trig identity that's basically cos. And remember, we can write it this way. The cos, put the 2 here between cos and theta, plus sine squared is equal to 1. The same thing. So, and we can do this for other powers too. So we can move this, let me use blue. We can say like cos of theta to the power 5 is the same as cos 5 with the theta. They mean the same thing. So some people like this notation better. I personally like this notation better. Now we could rearrange for cos or sine respectively. Let's say we took sine to the other side. So then cos of theta squared is just going to be 1 minus the sine of theta squared. And then we take that square root. So this would be plus or minus square root of 1 minus sine squared theta. And we could do the same idea for sine. So we could do the same idea. Let's say sine squared theta, bring it to the cos to the other side, 1 minus cos squared theta, and then take that square root. So that would be plus or minus square root of 1 minus cos squared theta. So again, this is nothing new. It's just the identity rearranged with the math that you know. So this is summarized here. And this is what I said, any power to the n, you can bring it between the cos and the theta. So nothing new, just summarizing. But like it looks different, right? Doesn't look, it kind of looks new, but it's not new. So let's write tan in terms of cos of theta. Okay. So we have our tan and we want to write it in terms of cos. So suppose we have this identity. We can divide both sides by cos squared theta. So we have the identity and we're going to divide it by cos squared of theta. We start off with something we know. Okay. So how do we do this? So we can divide cos squared theta plus sine squared theta. And this is equal to 1. But we're going to divide the left and right side by cos squared theta. Okay. Because we want it in terms of tan. And remember, sine theta divided by cos of theta is equal to tan of theta. So when we have something, it divides into each term in the numerator. So I'll just make another, write it out. So this would be cos squared theta divided by cos squared theta plus sine squared theta divided by cos squared theta equals 1 divided by cos squared theta. We know what this is equal to, the first one, hopefully. This is just going to go to 1. So this equals to 1. We have this. But what is this? Sine squared theta divided by cos squared theta. So we should know that this is equal to tan squared theta. Now we can rewrite. So this implies 1 plus tan squared theta is equal to 1 divided by cos squared theta. We can now rewrite tan in terms of cos by rearranging. Good. So we have tan squared theta is equal to 1 divided by cos squared theta, subtract 1. And then, of course, we have a squared here. So we take that square root to get rid of it. So we have plus or minus square root of all this. Okay. So we're almost there. Almost there. Now we can use secant is equal to 1 divided by cos to help simplify this. A little bit more. So I'm just going to write secant squared, this angle, is equal to 1 divided by this cos of this angle squared, which is exactly the same thing as if this 2 is brought in. So I'm just saying the same thing. Now we have 1 divided by cos squared theta is this part here. So we can therefore write tan of theta is equal to plus or minus square root of secant squared theta minus 1. So so we wrote tan is actually, so this is an identity. There's lots of identities in trig, unfortunately, like lots. There's like about 20 of them. You have a sheet that I uploaded on your Blackboard, but there's many of them, right? But if you kind of remember the basics, you can derive some of the formulas. Some are a bit more tricky. What about something like this? Ugh, right? This is more complex. How would we tackle this and simplify such an expression with like these tans and cosines? Ugh. It's not pretty, right? What do we do? So it's a little bit more complex, this one. So let's, how are we going to add this? Do we even have a common denominator? That's the first thing we do. Just like we did, the logic applies. So let's find a common denominator. To this. Now, 1 divided by 1 minus cos. If we want to add this, we expand this denominator by taking the first fraction and multiplying it by the denominator of the second fraction. So we just times 1 plus cos of this, 1 plus cos of this. Again, what is this trick that I keep saying to you? 1 plus cos divided by 1 plus cos is 1, right? So we can do this. We're not breaking any mathematical rules here. 1 plus the cos of this times now the denominator of the first fraction. So 1 minus cos of this. 1 minus. Okay, good. So that's the first step. We have a common denominator. Okay, check. Now we have to kind of do some math here, arithmetic. And simplify. So the first is 1 times the top. So that's just going to be whatever that top is. So 1 plus cos of this angle. We have a common denominator, so we can write it all out. Sorry, I'm going back to, I went to the bottom, now the top. So 1 times this is 1 plus cos of theta plus 1 times 1 minus cos of theta. If we wanted, we could put brackets around it. No need. Now the cos, subtract cos, that cancels. Good. Now we have tan squared of theta times 1 plus 1 is 2 divided by, and then we can multiply the denominator. So 1 times 1 is 1. 1 times cos, negative cos. So this is negative cos plus cos. So the middle part, if you apply FOIL, cancels. And we're left with the last part. Negative and times positive, cos times cos. This is cos squared, basically. So that helps us. It's a little better. What else could we do? We have 1 minus cos squared. What is that? What identity were we just talking about? So important. What is the side part? Okay, well, we can use this identity of sine squared plus cos squared equals 1. So therefore, we're going to have, so we have tan squared of theta times 2 divided by sine squared of theta. And we know tan is equal to sine divided by cos of our thetas. Therefore, tan squared is equal to sine squared of theta divided by cos squared of theta. So, okay. So this implies we have this tan squared. So we have this sine squared divided by our cos squared times our 2 divided by sine squared of theta. We see these cancel. Therefore, we have 2 divided by cos squared. So this ugly, kind of ugly, like expression simplified into 2 divided by cos squared theta. So it's kind of incredible that this expression reduces to this more simple term. It did. So let us remember the graphs of the cosine and sine functions. And if you can't remember them, please look at Google or Desmos. But let's just remember these. Or your textbook, of course, has these graphs. So it goes, they oscillate essentially from -1 to 1. And let me write the other one. Sorry, it just takes me a second to draw these. So at this point, it's pi divided by 2. This is the cos, the blue. At this point, it's pi. So cosine starts at like 1. It goes down to pi divided by 2. It crosses the axis. So it's 0 there, pi. This is like our 3 pi divided by 2, so on. And it goes all the way up here to 2 pi. Here it goes, negative pi divided by 2, this point. This is our negative pi. Negative 3 pi divided by 2. Sorry, I can continue drawing. And this is our sine. So what we notice is that the cos basically mirrors itself in that y-axis. There's a symmetry to it around that vertical axis. So if there's a symmetry along that vertical axis, what does that mean? That we've learned before. And this is a kind of like a rough sketch. And so we observe that the cosine is symmetric around that vertical axis. So it's an even function. So cosine is even function. So remember that even means that f of x, by definition, is equal to f of negative x. So there's that symmetry. So cos of theta is equal to cos of negative theta, because it's even. So that's what I'm saying here. Now, sine is sort of off a little bit. It's not, I'm sorry, I didn't draw it perfectly. Um, hmm. So is sine even or odd? Well, it's symmetric about the origin. So sine is actually, if I drew this a little nicer, and of course, check Google, check your textbook, check Desmos, type it in, be active, don't just watch or like listen to me. It's actually symmetric around this origin. So if we remember what an odd function is, it implies that when it's odd, f of negative x, the negative comes out front. So it's negative f of x. So sine of theta is just equal to negative sine of theta. Huh. Okay, which is what's written right here. So we can use like these properties to figure out what is tan to show that this property here. So we know by definition, tan is equal to sine divided by cosine. So this implies our tan with our negative theta is equal to, well, we just plug in the negative in. In front of the theta. We know that sine is an odd function, so we can write out the negative in front. We know cosine is even, so that negative goes away. And so it's equal to negative sine of theta over cos of theta, which is equal to just negative tan of theta. So we just showed essentially that tan of our negative theta is equal to negative tan theta. So is this even or odd? By definition. So our tan, because it satisfies which of our even or odd definitions? Odd, right? So it's odd. So tan, negative theta, let's say tan. Is an odd function. So what does this mean kind of for the graph? So the graph of tan is going to be symmetric. Well, they're both symmetric around the origin. And we drew that picture. Okay. Now, suppose we have an angle between 0 and pi divided by 2, which is 90 degrees. Let's say we have a right angle triangle. So let's draw like a little sketch. So it's 90-degree triangle where the length, we have C, the side opposite to this angle. Let's call this angle here theta. Opposite to it is B. And the third side is A. So this implies this angle here if we're talking about radians, it's just going to be pi divided by 2 minus our theta, whatever that angle is. And we know this from the sum of the interior of the whole triangle is 180 degrees. We know 180 degrees is equal to pi radians. So we know this is 90, or this is pi divided by 2 radians. So this is going to be pi divided by 2 minus theta. So I'm just talking triangles now in radians. Before I was talking degrees, I'm just saying the same thing in radians. Okay. So let's just repeat this kind of and focus in on this, on these sides, talking radians. There's a point. I'll make a second. So we have this angle before it's 90. We can say it's pi divided by 2 radians. This theta of A opposite here. Well, I'll write BC first. Here it's going to be theta, or pi divided by 2 minus theta. This is opposite, obviously. So let's express cosine, sine, and tan. It's essentially the same thing. So cos of this angle is, I can write SOHCAHTOA, or it's adjacent over C, our hypotenuse. So adjacent would be A divided by C. Our sine is opposite. So opposite was B. So B divided by C, and our tan. So our tan is our sine. So this is B divided by C, and divided by our cos. Our cos is A divided by C. See the C's cancel. And you get B divided by A. So it's exactly the same thing that we have been doing, sort of. So this time, we're going to be focusing on this angle pi divided by 2 minus theta, and express cos theta divided by 2 minus theta, sine, and tan in terms of the sides. So we're going to kind of do the same thing, except for we're going to look at this other angle. So we're going to look at this angle over here. So let me color code it. So we're going to look at this angle. Instead of this theta, we're going to look at pi divided by 2 minus theta. And it has radians, so you should probably say rads or something. You don't have to say it in between the trig. So let's look at that. So cos, I'll write over here. Actually, I guess I'll. So cos of pi divided by 2 minus theta is, well, if this is our angle and we're using a SOHCAHTOA, our adjacent side, it's just going to be adjacent divided by our hypotenuse. So our adjacent becomes something different. What does it change to? What is the adjacent side of pi divided by 2 minus theta? Where we're looking at this specific angle. It's B, right? That's our adjacent side. So it's B divided by C. And we can do the same idea for the rest. So when we're looking at sine, it's opposite of this angle is A. So we're going to be looking at opposite A divided by C. And then we do the tan, which is the same idea as before. Sine is A divided by C over our cos, which is B divided by C. C's cancel, so you get A divided by C. Okay, so we did the same thing. So we did it for theta, we did it for pi divided by 2 minus theta. We're just expressing this, and we can summarize this. So B divided by C, what is it equal to? Sorry, I have to flip back and forth. So B divided by C is equal to sine theta. So this cos of pi divided by 2 minus theta is equal to sine theta 2. What is the sine of theta divided by 2 minus theta is equal to A over C. A over C is equal to cos of theta, and 3. Okay, so tan of this, well, is equal to A over C. Oh, wait, should have been a B, thank you. I made a mistake there. This is a B, because these cancel, I don't know. So this is equal to A over B. So, but this is equal to B over A. So it's just 1 over the other. So 1 over tan. So this is going to be 1, whoops. 1 over tan. So what does this mean? Why did we do all this work? Why do we do this? Okay, so we see that basically it's like a transformation, like where we talked about graphs and functions. And we're inputting before like X, here we're inputting theta in either degrees or in this case, radians. And we see like there's the shift. So it basically tells us how it relates from sine to cosine. You see that their sine and cosine are related in a certain way by a shift of pi divided by 2. And it shifts pi divided by 2 to the left to get the cosine. So if you have the sine, you just shift it to the left, pi divided by 2, to get the cosine function, essentially. So they relate. So this is it again, just summarized. And here, this is in radians. And here it is in degrees, essentially. And you just can see this shift. And you can look back at the graphs to notice this. So let's do some more examples. So let's say we have the cos of 70 degrees. So this would be the same as cos of, let's say, 90, subtract 20. So this is the same as sine. of 20 by applying the formula. What about tan of, let's say, 30? Well, this is the same as 1 divided by tan of 60. And let's do a radiant example. So cos, let's say 3 pi divided by 8 is going to be the same as cos pi divided by 2 minus pi divided by 8, which is equal to sine of pi divided by 8. So they relate to each other, sine and cosine. So I'm just applying what we just derived to something with numbers in it. Okay, so let's consider this unit circle, 1, 1, negative 1, negative 1. And we have, so let's say a point on the unit circle with a particular angle. So this point, as you remember, this is our cos and sine of this particular point. We know this. Now let's consider what happens if we add pi, or this 180 degrees, to our angle. Let's say we have it in radiant measure. So what happens is we rotate it, this angle, plus we add that pi, so it's going to go over here. What is this point over here? Well, you could see that it's just going to be negative cos theta, negative sine theta. Because it's like, or just adding, so it's like, you know, doing a 180 degree turn, you know, positives and negatives. It's like you're going in one direction, now you go in the opposite direction by adding 180 degrees. So you should be able to kind of see that. So what are the coordinates of the endpoints of this radii? Because if this was our x or cos, then if you add it, it's just going to be negative. The sign is obviously in the negative directions. So what are these points? Sorry, it's a. This point is also cos of this angle plus pi, sine of theta plus pi. So it just means that the cos of theta plus pi is equal to negative cos. And sine, this angle of theta plus pi, is equal to negative sine. So if you add pi, you get negative. Those are the coordinates. So this is what I'm saying right here. Just repeating it. And from like those two identities, you can derive what tan is essentially. So if you remember like a little picture of what tan is, it basically has those vertical asymptotes. Like this is just a little sketch. We already drew this before. It looks like this. at pi divided by 2 and negative pi divided by 2. So what does tan that look like? Well, tan of theta plus pi is equal to sine. And we just use by definition, sine divided by cosine. But now we substitute plus pi, theta plus pi. We know sine is equal to negative. Like when it's theta plus pi, we can substitute this part in. Cos of theta plus pi is just the cos of it, negative cos. Negative and negative cancel, and you get tan of this angle. So then we get, of course, our definition. So of course we see this tan theta plus pi is equal to our tan of theta. We kind of like derive more identities. I'll just say for this part, just see your notes of we've done this several times, notes for what the cosine, sine, and tangent functions are, and please look at the graphs of these functions to see the effects. Remember, like cos and sine, their periods were 2 pi, tan was pi. Just a reminder to go look at these. Now we could observe that the cos and the sine functions have like this period, essentially 2 pi, and the tangent function has a period of pi. So we can obtain the following identities, that the cos of the angle plus 2 pi is equal to the cos of that angle. That it has like this kind of pattern and it repeats. So we can add essentially this. Same with sine. And tan, the period was just pi. So we can add multiples of pi to the tan. And the other two, we were just adding multiples of 2 pi here. So it's also equal to the same as cos of the angle plus 4 pi, etc. So I'll just make a little side note. So let's say a function is periodic with this period 2 pi means that the graph repeats itself every 2 pi units in that x coordinate. So we know cos, sine, and tan. They're all periodic functions, but they have different periods. Cos is, and sine, their periods are 2 pi, tan is pi. Let's look at examples. So the cos of, let's say, pi divided by 6, we add plus 2 pi. What is this equal to? Cos of pi divided by 6. Same thing, which is also equal to cos of pi divided by 6 plus, let's say, 2 pi plus 2 pi. They're the same thing. You keep adding 2 pi to it, you get the same answer. We could even subtract it. You could say cos of pi divided by 6 minus 2 pi. They're all the same thing. What about tan? So let's say we have tan pi divided by 8 plus pi is equal to tan of pi divided by 8. And we could subtract it too. So pi divided by 8 minus pi, or we could add multiples of this just pi. So plus pi, plus another pi, etc. So I'll just make a little note here. So adding or subtracting any multiple of 2 pi to the angle does not change its sine or cosine. Value, essentially. Should write value. Same with tan, almost similar. So we could adding or subtracting any multiple of pi to the angle, of course, does not change it. So it doesn't change the tangent value. So because the period here, of course, repeating myself, but the period here for tan is pi. And the period here for sine or cosine is 2 pi. This is tan. So if they change. And I think we can see that with the graphs, with the pictures. So this is just the period. Can you see that? Is it clear? Am I writing? So can you kind of see it? Sorry. Okay. So algebra and geometry. So inverse trig functions. So we want to define inverse functions on the cosine, sine, and tangent functions. Now, what is the problem, right? Like when we're talking about sines, cosines, and tangents, right? How can we define the inverse? What did I say that an inverse function has to be? So if we remember, and like what a one-to-one function is or is not, let's say we have like this little graph here. Is this a one-to-one function? No, right? So if we remember and recall, we draw this line, it intersects this graph. Therefore, this is not a one-to-one function. Why? Because some, let's say some horizontal line crosses this graph in more than one point. Just as a reminder. And cosine, sines, and tangents, they're not going to be one-to-one functions over the entire domain, right? So we know this because the cosine function, just like a little quick sketch of it, something like it goes up and down and up and down, right? So it oscillates back and forth, back and forth. It starts at 1 here. So if we draw a horizontal line, we have a problem. So we can clearly see, I'll just make a little note. We see that this cosine is not one-to-one. Neither is sine, neither is tan. So neither is sine or tan. So unfortunately, so to define this inverse function, for cosine, sine, and tangent functions, we need to do extra work. So we need to do more work for these cosine and sine functions, because on the whole domain from negative infinity to infinity, we see we have a problem. Okay. So we can define this thing. The idea here is to define the arc cosine and consider the cosine function on the domain. So if we drew this graph for the cosine, now we stop it. It continues on the graph, but let me, this point here is pi divided by 2. This is pi. So the idea is we're going to graph this cosine function on the domain and we're going to restrict this domain. So on a restricted domain from 0 to pi. Now is this function 1-to-1? Yes, right? We could draw a vertical line test. So this is almost done. One second. So this is 1-to-1 function. So we can observe this on this interval, that this is 1-to-1, because so then we can define that inverse. I'll just write one more. I think I have one more minute. So let me write a note. So we can define this arc cosine of t by this inverse. So all we had to do was remember that the domain of the inverse is the range of the original function.